I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 3, Making Measurements. In this lecture, I'll talk about the various ways that astronomers make measurements of the objects that we see in the sky and suggest a handy way of getting your head around the size and scale of our solar system and universe. So we look up into the sky and we make observations about the things that we see. We notice the moon and the sun and the stars, and notice that some of the stars wander and that they're the planets that we see in the sky. Naturally, astronomers, after making these general sort of gross observations, would like very much to quantify things, to be more precise in our description of the things that we see in the heavens. One complicating factor is the whole spherical nature of the thing. Consider that you're standing on a sphere that's revolving and orbiting the sun. The positions in the of everything that we see in the sky, for that matter, are complicated by the fact that the Earth is in motion itself. And so the steps that we take to precisely locate objects in the sky are subject to the consideration of the motion of the Earth itself. Because also the spherical nature of the Earth and our singular view of the heavens surrounding us, the notion of angles becomes extraordinarily important in astronomy. We measure angles naturally in degrees, with 360 degrees in a circle, which is a throwback to the interest that our ancestors had in sexagesimal number systems based on 60. And in fact, every degree of the 360 degrees in a circle is composed of 60 subintervals. These are called minutes. Now, they're not the same minutes as the minutes that we have for time, but 1 degree is equal to 60 arc minutes. That is, 1 arc minute is 1/60th of 1 degree, and the symbol for that is a 60 with a prime. Now, to me, the prime often means feet. I just have to remember that in astronomical concept, 60 with a prime next to it means 60 arc minutes. Each one of these arc minutes is divided into 60 intervals known as arc seconds. That is, 1 arc second is 1/60th of 1 arc minute. And that's given as 60 double prime. Now, to me, that looks like inches. Again, remembering in the astronomical context, this is 60 arc seconds. So I've taken the 360 degrees in a circle and divided by 60 and divided by 60 again. That means that the angle measures that I've come up with, particularly the arc second, are small indeed. In fact, if I look at the 360 degrees of arc in a full circle, and that's shown here on the lower left, and I look at an angle that subtends 1 arc degree, that 1 degree shoots out of the circle here like a ray, getting wider and wider as it goes. If I zoom in on that, the square that's on the upper left, I zoom in and see 1/60th of that arc degree, which is then 1 arc minute. Zooming in again, 1/60th of that arc minute is 1 arc second. So I find that an arc second is an angular measure that's so fantastically small that I cannot even draw it on my diagram of the 360 degree circle. Why is it that I should need angular measures that are so spectacularly small? Well, the fact of the matter is, if I look up in the sky on a clear night, I see so many objects so close together that their angular separations are very small indeed. And it turns out that even though these stars appear to be generally fixed in space, that as I watch them move, they shift from side to side at angles so very small that in most cases they weren't observed until mankind first invented powerful telescopes. So these very, very small angular measures are a natural consequence of the profusion and subtle motions of objects that we see in the sky, and so as we read about and study astronomy, we're likely to encounter measurements of arc degrees, arc minutes, and arc seconds. If I'm just going to go out and do some backyard astronomy, however, not using a telescope, I might go out on a given evening and be told that I can look for these objects in the sky, and the astronomical forecast that I'm reading might say that an object is located 12 arc degrees from the moon on a given evening. Well, I can imagine at that point breaking out my telescope and doing some sophisticated measurement or using some sort of instrument, but in fact my hands will do just as well. A typical adult human hands works out this way. You see, the width of the palm is about 10 degrees, while the width of the tip of the index finger is about 1 degree. The knuckles are 3, 4, and 6 degrees successively. And so I can, just holding my hand up to the sky, can make estimates of the angular positions of objects. And in a minute I'll talk about how this might be particularly useful. You'll notice as a test of this that if you go outside and find the Little Dipper, Ursa Minor, and look up at it, the distance between the pole stars, which are the two stars at the end of the Dipper there, is approximately 5 arc degrees. And so you can hold your hands up and verify that in fact it's so, that's about 5 arc degrees. It turns out that the angular size of the moon and the sun in the sky, also about 5 arc degrees. It turns out to be meaningful as well, that the sun and the moon subtend about the same angular separation as viewed from the Earth. When we make measurements of the positions of objects in the sky, for example, if we're doing amateur astronomy and there's an object that we'd like to see in the sky, for example, we have a new telescope and we'd like to have a look at the Pleiades. Well, we look it up in our astronomical catalog and it tells us the position of the Pleiades in the sky according to two coordinates, celestial coordinates, called the right ascension and the declination. It's important for us to understand roughly how these measurements work. The idea is this: if I extend the surface of the Earth out into space an arbitrary distance, we call this the celestial sphere. The idea is that every astronomical location has a position on this celestial sphere. For stars and galaxies and other objects very, very far away, their position in the celestial sphere is fixed. For planets and our sun and asteroids and satellites and so forth, their position in the celestial sphere is not fixed. Nevertheless, each one of them at any given time has a right ascension and a declination. Right ascension and declination is not altogether different from latitude and longitude. There is a line on the Earth that is considered to be 0 longitude. We call that the Greenwich meridian, because it happens to run directly through Greenwich, England. And then we measure angular distance 360 degrees around the Earth in a sequence of vertical lines called the longitude. Using the equator as 0 and positive angles up from the equator towards the North Pole, then we have the positive latitudes. Below 0, we have the negative latitudes. And so any position on the surface of the Earth can be specified by its longitude and its latitude. Similarly, the position of any object on the celestial sphere can be specified by the right ascension and the declination. The declination is easy to understand because it works just like latitude. Imagine that we take the equator of the Earth and extend it out into space until it intersects with the celestial sphere. The declination, then, is an angle measured up from that line on the celestial sphere called the celestial equator, coincident with the Earth's equator. An angle measured up or down. Angles measured upward in the northern hemisphere towards the north celestial pole, which is at the top of the celestial sphere along the axis of the Earth's rotation. Those angles measured upward are positive angles. Angles measured lower are negative angles. So this gets really simple, because if I'm told that I can expect to see a star in the sky at a declination of 20 degrees, then I'm simply go outside and from the horizon I could look up from the celestial equator and measure with my palm twice, and that would be about 20 degrees of declination. Right ascension is a little bit trickier because the celestial sphere and the Earth move independently of each other because the Earth is rotating. So I could, if I simply did latitude and longitude, I would find that I would be in trouble, because although an object might be over a particular latitude and longitude on the Earth on any given day, or any given hour, any given second, the Earth then rotates and the object appears to move away. The way that we experience this is that when you look up in the sky through the course of the evening, the stars move. They rise in the east and they set in the west, just as the sun rises in the east and sets in the west, and the moon rises in the east and sets in the west, and all of the planets rise in the east and set in the west. This is because the Earth is rotating as the celestial sphere remains constant, fixed in space. Therefore, in order to compensate for this rotational motion of the Earth, the right ascension is measured from the position in the sky, or the exact position in the sky, of the sun on the vernal equinox. At that instant of the vernal equinox, the sun is directly above the equator at a very particular point in the sky. Right ascensions are measured from there, where the Earth rotates 360 degrees in 24 hours. As a result, right ascension is measured out in hours, minutes, and seconds of rotation from the vernal equinox. Now, just a moment ago, I mentioned hours, minutes, or I at least mentioned minutes and seconds of angle in terms of our angular measurement, arc minutes, arc seconds. The minutes and seconds of right ascension are not arc minutes and arc seconds. They're simply the 24-hour day divided up into 360 degrees. So right ascension hours, minutes, and seconds are in fact hours, minutes, and seconds of the Earth's rotation. This way, whenever you want to make observations from your hometown and you open a book and get a right ascension and a declination, you simply have to make a correction for the time of day at your location, adding or subtracting from the right ascension and declination accordingly, in order to exactly locate the positions of objects in the sky. At first blush, this may seem a little complicated, but it's inevitable for to have a precise, immutable location of objects in the sky. So here's what happens with our celestial sphere. We stand on the Earth and rotate as the celestial sphere remains stationary. But here we'll imagine that the Earth is stationary. You see the little person standing on the surface of the Earth in a northern latitude at apparently, according to this diagram, 35 degrees north latitude. And from that person's point of view, they're absolutely stationary as the celestial sphere rotates above them according to the arrow. Therefore, every object that is in the east will rotate overhead and set in the west as the Earth rotates under the celestial sphere, or, from the point of view of the observer, the celestial sphere rotates above the observer. This has an interesting consequence for the motion of stars in the night sky. There are stars near the pole star, the axis of rotation, which is naturally Polaris at the present time. Near the axis of rotation in the upper right of the diagram, there are stars that will rotate on the celestial sphere that will never fall below the horizon. That is, they'll never get low enough that the Earth itself obscures the view of the observer. And those stars never set. Stars between there and the limit of vision towards the south will rise and set according to the rotation of the Earth. But if I'm standing in a northern latitude, even this at 35 degrees, there are stars and objects on the celestial sphere near the south celestial pole that will never rise and never set. And if you're a person who has never been to the southern hemisphere, then there are in fact stars in the sky on the celestial sphere that you have never in your life seen. And in fact, there are constellations that are not visible from the northern hemisphere, but are visible from the southern hemisphere. So you see that there are a lot of issues associated with what you can see and where as the Earth rotates under the celestial sphere. When we measure distances in astronomy, we naturally are considering distances very much larger than the distances that we encounter in everyday life. Meters and kilometers are not terribly useful, except if I'm talking about the orbit of satellites around the Earth. So for this purpose, we've invented units of a much larger scale, such as the astronomical unit, otherwise known as the AU. It turns out to be 1.496 times 10 to the 8th kilometers. And that may at first sound very arbitrary, but the truth of it is that this is the closest or the most precise measurement that we have of the average distance between the Earth and the Sun. This astronomical unit tells us that if the Earth-Sun distance is 1 astronomical unit, we can use that as a comparison for all of the other distances in the solar system. And in fact, it's true that in the history of astronomy, when Kepler first discovered the relative sizes of the ratios, or discovered the ratios of the orbits of the planets around the sun, he was unable to determine the actual distances in meters or kilometers or feet or whatever he would have, whatever unit he would have chosen, because he simply didn't know the Earth-Sun distance. And so he measured everything out using the distance between the Earth and the Sun as 1. And today we call that the astronomical unit. If I'm talking about the distances between stars, however, it turns out that the astronomical unit is quite small indeed, and a better unit of measure is the light year. According to its name, it's easy to confuse this with a measure of time, but in fact, the light year is the distance that light travels in 1 year. Light travels at an extraordinarily high velocity, 180 million miles an hour, or 3 times 10 to the 8th meters per second. So it gets very, very far in a short period of time. In particular, in 1 year, light travels 9.46 times 10 to the 12th kilometers. At this distance, we put the distance to the nearest star, which is Proxima Centauri, at about 4 light years away. So the light year is a convenient measure for talking about the distances between stars. There is another unit of measure called the parsec, which is just about 3.26 light years. It's strange that we should have a unit called the parsec, which is so similar to the light year, but in fact there's a decent astronomical reason for this. The definition of the parsec is the distance from the sun for which the orbit of the Earth, which is 1 astronomical unit in radius, would appear to subtend an angle of 1 arc second. Now remember how extraordinarily small the arc second was. So indeed, this diagram that I have here is not to scale. The parsec is significantly further away, more than 3 light years away, from the sun, so that if you looked back and viewed through a telescope and measured the radius of the Earth's orbit from that point of view, it would subtend an angle of 1 arc second. This is useful because we use the angular sizes of objects in order to determine their distances and or actual sizes as a regular practice in astronomy. So the parsec is a convenient unit of distance in that way. You probably are already wondering about the appearance of the Millennium Falcon from the film Star Wars at the bottom of the slide. The reason why I put this here is that it's commonly known that in the first movie, the pilot of the Millennium Falcon bragged that the Millennium Falcon was the ship that had made the Kessel Run in less than 12 parsecs. Probably when the script was written for the Star Wars film, the writer, in principle George Lucas, mistook the unit parsec for a unit of time, because the sec at the end of parsec is similar to seconds. Nevertheless, astronomers sort of balk at this line in the movie because it seemed that he was implying a unit of time. Later on, writers associated with the canon of Star Wars fixed the problem by saying that what Han Solo was in fact saying was that he had done a smuggling run through some shipping lanes in space in the shortest distance possible, which would naturally imply the shortest time. The reason why the distance mattered is that there were some black holes involved, and if you get too close to the black hole, you could put yourself in a situation where you cannot escape. And so the ship would have to be very fast indeed in order to make the closest approach possible to the black holes, and therefore travel the shortest distance from the beginning of the run to the end. And so his statement that he made the run in less than 12 parsecs could be a legitimate description of the performance of the spacecraft. Or it simply could be a lame attempt on the part of the imaginations of writers to compensate for a gross flaw in the technical aspects of the script. Either way, Star Wars is cool. So when I'm measuring the distances, I want to get out there and measure the biggest thing that I possibly can, which is the universe. How big is the universe? Well, in answer to that, it's 10 billion centimeters across. Naturally, centimeters are not a good unit for measuring the size of the universe, because when you write that out with all that zeros, it's disgusting. But I've learned that I can write the number in scientific notation and say it's about 10 to the 28 centimeters. Still, not a number that I can sort of get my head around. 10 billion light years, however, is a number that's easy to say and to think about when I consider it's about 4 light years to the nearest star. Then 10 billion light years is pretty darn far away. This works out to be 6,000 megaparsecs, 10,000 parsecs in a megaparsec. And so you can imagine that the units that cosmologists use to describe the size of the universe and the distances between galaxies are in megaparsecs. As you read and study astronomy, you're likely to run into the unit in megaparsecs and understand that when that unit is used, the distances that are being described are quite large indeed. Here I have a handy guide to the scale of the universe, and in a moment you'll recognize how horrible that pun is. The idea, and I keep this in mind myself all the time to think about or to describe to others the size of our universe. Imagine that the Earth is the size of your fist, and we'll scale everything else accordingly. If the Earth is the size of your fist, then the moon is the size of your thumb 3 meters away. I often demonstrate this in classrooms by having a student raise a fist in the air and then hold up my own thumb 3 meters away. The reason why this is remarkable is that sometimes as an exercise, I'll ask students to take out a piece of paper and draw on the paper a diagram of the Earth-Moon system to scale. Try and get the sizes and the distances right, and everyone fails at it. Because if you hold up a fist and hold a thumb 3 meters away, which you can't do yourself because your wingspan is certainly less than 2 meters, but if you hold up your fist and your thumb 3 meters away, it sets a dramatic scale to the Earth-Moon relationship that is not what I think most of us expect. If that is the relationship with the Earth and between the Earth and the Moon, the Earth is the size of my fist, then the Sun is an 11-meter diameter ball located at City Hall. And by City Hall, I mean that I would be giving this lecture at Drexel University, and City Hall is some 20 city blocks away. So if the Earth is the size of my fist, the Sun is about 20 city blocks away and is an 11-meter diameter ball. So it's enormous in size. And naturally, we expect that to be the case since the mass of the Sun represents 99% of the mass of the entire solar system. On this scale, Jupiter is a ball 1 meter in diameter located in Cherry Hill, New Jersey, which is across the river in New Jersey. Pluto is the size of your fingertip in Central Park, Manhattan. The center of our galaxy is still 2 billion kilometers away. So even if I make the Earth the size of my fist, this guide to the scale of the universe breaks down very rapidly till once again I'm involving sizes that are difficult to get my head around, because the center of the galaxy is 2 billion kilometers away and the edge of the observable universe is still 800 trillion kilometers away, even if I reduce the Earth to the size of my fist. And so the ultimate truth here is that there's no way to devise a scale for the universe that'll make it work out. By the way, if you don't live in the Philadelphia area, you might want to look at all of these measurements and see if you can scale it accordingly. If you measure the size of your fist and you know the size of the Earth, 6,400 kilometers in radius, 12,800 kilometers in diameter, then you can figure out how many kilometers it is and set up your own scale according to the geography of the own area wherever you happen to live. Nevertheless, it's fun to get out with the kids, and instead of making the styrofoam ball solar system where everything's out of scale and things are barely even the right color, to set up the scale and see how spectacularly large this is. A question that I would ask you is, if the Earth is the size of your fist, then how big are you?